Okay, hi everyone. So let's proceed with the next part of the lecture on operational amplifiers non-linear applications. So in the previous videos we have looked at the linear applications, and now we'll look at the non-linear. So for the non-linear, basically we are going to cover comparators in the first part, and the second part will cover the Schmidt trigger. So two main applications, and for comparator there are two types of comparator that we're going to look at. We're going to look at the inverting comparator, non-inverting comparator first, non-inverting comparator, and then the second part we're going to look at the inverting comparator. Okay, and then the next lecture we're going to look at the Schmidt trigger. So what are comparators? Comparators is a certain configuration on our op-amp. It has two inputs and one output. The operation is a basic comparison. So basically what we want to do is we want to compare the values on the minus input terminal and the plus input terminal. The output swings between its maximum and minimum voltage depending on whether one input is greater or less than the other, which is called the reference. So we are looking at the output terminal here, and the output terminal there, the output will depend on the comparison, the difference between Vref and Vin. So the output is always a square wave where the maximum output is Vsat. Okay, so V plus Vsat is this 10 volt here, for example, and then negative Vsat, the negative supply that we give to the op-amp. So essentially the comparative circuit, well, what we want to do is this is our input here. So our input here, we supply a sine wave on the input. Okay, on here we apply the sine wave on the input, and we are expecting a square wave on the output. So sine input, and then we have a square output here. And this V out here is corresponding to our output value. So let's look into more detail here how we can design construct the comparator. So in the comparator here, what we have in the basic op-amp, what we have is we know that V out is A V plus minus V minus, as given by this equation here, and we know that A here is infinity, very large, the open loop gain of the op-amp, and therefore will become maximum, that is either at plus VO set or minus VO set. Since this is very large, V out is going to be limit to plus minus VCC. And here is the transfer characteristic. So you can see that what happened to our V out when we supply our V in. Okay, so V difference. Okay, when we supply the difference between V plus and V minus, you can see what happened to V out. And here it says that if input V plus is greater than V minus, we're looking at here. If V plus is bigger than V minus, then V out is equals to positive VO set. So positive VO set is here, and negative VO set. And if the input V minus is greater than V plus, okay, looking at V minus is greater than V plus, then V out is simply going to be negative VO set that we set on the supply of the op-amp. And looking at this graph here, the transfer characteristics, so here you're looking at the transfer characteristics of the voltage comparator, and we can see here that if V in, so V plus minus V minus is greater than 0, okay, at this condition, we can simply say that our V out is actually equal to V max, where you can say here is V plus is greater than V minus. So here is saying that if V plus is greater than V minus, then our V out is V max. And on the other hand, if V plus is less than V minus, okay, the condition that V plus is less than V minus, and V out is negative V max. So let's look in more detail here. So in the comparator, what we do is this is Vref. So Vref, we're going to put it 6 volt on Vref. And then we are going to put plus minus 15 here, plus minus 15 volt on the supply of the op-amp, and we are going to supply a sine wave on the input. Okay, we are going to supply a sine wave on the input. 6 volt sine wave, 10 volt peak to peak, 10 minus 10, 15, and what is our V out here? What is V out going to look like? So V out is going to look like this. Okay, so V out is going to get a square wave, and how is it going to look like actually? So we know that here, if we put 6 on the negative terminal of the op-amp, then we know that if Vi, okay, we put a negative terminal, so this is a non-inverting, this is called a non-inverting comparator, non-inverting comp. If Vi is greater than 6 volt, then V out is equals to 15 volt. If Vi is less than 6 volt, V out is going to be negative 15. So this is the characteristics that we saw in the previous slide. So we are looking here that if Vi is greater than 6, less than 6, so at the moment that our input is less than 6, okay, that's the moment when our input is less than 6, then we know that our V out is going to be constant negative 15 as given here. And at the same time now, if we increase our V in, to be greater than 6, okay, so at the moment that our input is more than 6 volts, then we know that our V out is going to be a constant 15. So this is what happened here, that at the moment that our input is greater than 6, our V out is going to be 15. And the moment that the input is less than 6, okay, less than 6, then we're going to have a constant negative 15 on the output. So this is a non-inverting comparator. So looking at more details on the non-inverting comparator here, so we can also do a setup with some resistors. So basically the theory on the non-inverting comparator, that the output goes to plus V sat when input Vi is greater than the reference voltage. Okay, and in this case Vi is here, and the reference is going to be on the negative terminal of the op-amp. So if you put it on the negative, it becomes a non-inverting comparator. Okay, so Vref on negative, we have a non-inverting where the output goes to Vsat if Vi is greater than the reference. The output goes to negative Vsat when Vi is less than the reference. Okay, so let's look at the example here. So what is Vref? So Vref here is just going to be 12 10 over 10 plus 10 equals to 6 volt. Okay, so basically Vref is a voltage at the input terminal with the ground reference from the input terminal to the ground, and we have 6 volts equals to 6 volt here. So then we can say that V out, okay, is going to be a constant 12 volts if V in is greater than 6 volts. Okay, and then V out is equal to negative 12 if V in is less than 6 volts. Okay, based on the calculation there. So here's the characteristics here. We can see here that Vi greater than 6 output to 12 volts. Okay, if Vi is less than 6, and the output is constant at negative 12. Okay, let's look at the inverting. So just now we look at the non-inverting. So the main characteristics of the inverting op-amp is that we have Vref on the positive. Okay. So if your Vref is on the positive, then inverting. So Vref on positive terminal, positive terminal. So Vref on positive terminal is an inverting. So in the inverting, the characteristic is a little bit different. So we can see here that for inverting, the output goes to negative Vsat when Vi is greater than the reference voltage, while the output goes to plus Vsat, input is less than the reference voltage. So here we have 12 volt here, and here is also 6 volt. Okay, Vref is also equals to 6 volt based on the voltage divider and the 12 volt that we've seen in the previous slide. So if our Vref is 6 volt, then we have a positive connection for the ref, and Vi is connected to the negative. Then we can say that V out is equals to negative 12 volt if Vi is greater than 6 volt. Okay, it's greater. Then V out is plus 12 volt if Vi is less than 6 volt. So you can see here that if Vi is small, we are going to give a positive output, and Vi is big, we are going to give a negative output. So it's the other way around, so the invert of the comparator. So you can see here that Vi is greater than 6, output negative 12. If Vi is less than 6, we're going to output plus 12. Okay, and the main characteristic is that we have a positive terminal on the VREF. So just a recap on the comparator, let's look at the exercise here. Given the connection as given here, draw the output waveform, V out, for the given sine input as shown. In the case of VREF equals to 0 and the VREF equals to Vm over 2. So case 1, VREF equals to 0. Case 2, we have VREF equals to Vm over 2. Okay, and we see here that the VREF is actually connected to a positive terminal of the op-amp, and therefore here we know there's going to be inverting, it's going to be the inverting comparator. Okay, so it's an inverting comparator, and inverting comparator with the reference of two cases. If 0, what's the output? If it's Vm over 2, what is your output? And here is the input, so the input is given as given here. So if we supply sine wave, plus minus Vm, and what should happen to our V out here? Okay, so from here we can see that this is an inverting, so we know that V out is going to be equal to VCC if Vi is less than our VREF. Okay, and then V out is negative VCC, okay, negative VCC if Vi is greater than VREF. Okay, so VCC is VOSAT, okay, so VCC or negative VOSAT, our assumption there, and then and VREF, we have two cases. How can we draw the output waveform if VREF 0, and how the output waveform will change if our VREF is Vm over 2. So we can see in the solution here. So in the first case, this is VREF equals to 0, and VREF is equals to Vm over 2. So if VREF equals to 0, we can see that if the input, okay, so we have V out is equals to negative VCC, V out equals to negative VCC if V in is greater than VREF. Okay, V out is plus VCC if V in is less than VREF, and here we have VREF is equals to 0. Okay, so let's have a look. So Vi is greater than VREF. Okay, so here is our Vi. So is Vi greater than VREF? Yes, up to this point. Okay, and up to this point VREF here is 0. So Vi is actually greater than, and then we have that this condition, Vi is greater than VREF, and therefore our V out is going to be a constant VCC. And what happened here? So in this case, okay, here you have Vi is less than VREF. Okay, so Vi is less than VREF. So what happened is Vi is less than VREF. Then our output V out is equal to plus VCC. Okay, and here is going to be minus VCC. Let's look at the second case. The second case is the same. So we can see that our VREF now is Vm over 2. Okay, our VREF now is Vm over 2. So, and whenever that your input is greater than Vm over 2, we are going to have our output is negative VCC. And whenever that our Vi is less than VREF, okay, Vi is less than VREF, and we can see that our V out is going to be equals to VCC, and so on. Okay, so that's finished with the comparator part. In the next video, we'll look at the Schmidt trigger.